All right, reaction mechanisms. Here we go. A reaction mechanism is the steps by which the reaction occurs. We've looked at mechanisms before in terms of Hess's law and K and flipping and merging them to the overall reaction. We've looked at them before, but we didn't really define exactly what they were. So each series, each step is called an elementary reaction that occurs in one single step or event. It's usually like the most reduced form of that particular reaction, where it's sort of like a formation type deal where you're forming a compound and things like that. Each step within the mechanism is like its own little reaction with its own activation energy and its own rate law. But the rate law of an elementary step can be deduced from the equation of the step. So for example, we have this overall, nice overall reaction, and I'm going to show you a proposed mechanism of two steps here. We'll eventually get to getting to the rate law for the overall, but for the individual steps here, in order to write the rate law is going to be dependent on the concentration of the reactants. So in this particular case, for number one, it's going to be the concentration of the hydrogen, the concentration of the iodine monochloride there. So what would be the rate law for this individual step here? It would look like this. Rate equals the rate constant 1, assuming that's for step 1, that's the rate constant for step 1. It's going to be the concentration of the hydrogen times the concentration of the iodine monochloride. Now, they are both given first order reactants there because there is 1 mole of each here in the step. So they get first order because there's 1 mole of each one. So if that is the rate for the first step, I'm sure you can imagine the one for the second step here is going to be dependent on the HI and the iodine monochloride. Except for, because this is a different step, its rate constant will be different because each one has its own individual rate constant. So that we put that as K2. But there's 1 mole of the HI, there's 1 mole of the ICL, so they also get first order reactants written from the mechanism. That's how you do it. It's based off of the mole relationship in the mechanism. Later on, I'm going to show you how to merge these things to get the overall. And when I talk about the overall, it would be the rate law for this entire merged reaction here. Let's start with the elementary steps. Each individual elementary step has its own rate law, has its own rate constant. And it's the concentration order of reactants in the rate law is dependent upon the moles in the reaction there. Now, the molecularity, number of reactant particles in an elementary step is called its molecularity. So, a unimolecular mechanism step involves 1 particle. So you're starting off with just 1 substance as the reactant. I'm sure you can understand that the bimolecular step involves 2 particles. Bi means 2, like bicycle, so you have 2 reactants. Just realize, though, that sometimes if it's bimolecular, it could be the same reactant reacting with itself and running into itself. So it doesn't have to be 2 completely different substances. It could actually be, you know, NO2 runs into NO2 and creates a different compound. Termolecular involves the 3 different things reacting and colliding. 3 different particles have to collide here, so this is why it's rare. It doesn't happen so often, where you have 3 that collide and have bond breaking, bond forming all together. That's going to be termolecular. Here's a nice little chart that kind of sums everything up for you. As you can see, the unimolecular, just the A, Bi could be A plus A or A plus B, so it could be the same substance or different particles, different chemical species. And then, of course, the termolecular, you've got different variations here. Could be 3 of the same, 2 of the same, and 1 or 3 difference. But they're all pretty rare because, the idea that 3 things are going to hit and collide at the right orientation to have bonds breaking and forming and getting an intermediate out of that is rare. Now, exercise 1. What is the rate law for the elementary step? Chlorine plus carbon monoxide gives you this ClCO compound. Take a moment to answer this. Which one's the rate law for this elementary step? A, B, C, or D? Yes, going to be D. Very good. It has, this is the reactant, this is the reactant. They're both 1 moles. There we go, in there. Now, what is the molecularity in looking at those reactants? We only have 3 choices. It's either uni, bi, or ter. Bi. It's got to be bi, yes. This is bi-molecular. Why is it bi-molecular? Because there's 2 reactants. 2 reactants. Very good. All right, now we're getting into the more difficult stuff. Now we're going to combine these elementary steps because most of the mechanisms are going to be multi-step. They occur by a series of elementary steps. Now, one thing that you're going to see in these mechanisms where you have a series of steps are things called intermediates. I've talked about them before because they're very unstable. They're the in-between. In that hill part of the potential energy diagram, that in-between, we have a lot of intermediates forming that are not stable. So they are formed in one step and then they are consumed in the next step. So they're formed in one of the steps of the mechanism and then they get consumed as a reactant in another step. Now what they do in order to really, because these are proposed mechanisms, people, look at the different experimental data and they look at the rate law and all of that and they propose different mechanisms. Now, who decides which one's the actual mechanism and which one isn't? Well, a lot of times they don't really know. They just have them as proposed. However, if they can detect a little bit of the intermediate, that, of course, gives more support to a certain mechanism. And the intermediate portion, when they try to detect it, obviously it's going to be very small because it's an unstable compound, so it doesn't usually stick around. But if they can detect even a little bit of it, it supports the idea that that is the appropriate mechanism for the rate law, for the overall reaction. Another thing you'll see in these mechanisms are catalysts. And the way we look at the catalyst is it's a reactant or it's used at the beginning of the mechanism and then it's formed at the end of the mechanism. And it remains unchanged. Remember, the enzymes, they just help speed it up. They don't actually really, aren't part of the bond breaking, bond forming, changing itself. So it's there at the beginning, it's there at the end, and it remains unchanged for the catalyst there. Now we're going to look at an example here. Looking at a mechanism. How are we going to propose our rate law from our mechanism? Well, let's look at this one here. Nitrogen dioxide plus carbon monoxide gives you nitrogen monoxide and carbon dioxide. It's a 2-step mechanism, and they gave us the particle diagram for it. So if we're looking up here, we know the mechanism. Another key piece of information, they have to tell you which step is the slow step. So the first step here we're saying is the slow step, the second step is the fast step. That's important information too. So the first step is actually the slow step, the second step is the fast step. So before we get into writing the rate law, let's look up here and see if we can find any intermediates or any catalysts based off of what we just defined. So any intermediates? Something that is formed and then consumed, doesn't stick around, not a part of the overall balanced reaction. Which chemical series up here would be an intermediate? Well, if I'm looking here, the NO actually is a part of the overall, so that one does stick around here. It is going to be part of our overall balanced reaction at the top, so that one is not an intermediate. Which one would be the NO3? Very good. This is your intermediate here. As you can see, it is formed in the first step. It's part of the products. Then it gets consumed over here in the second step. So it actually cancels out and is not a part of the overall balanced reaction. Does that make sense? Kind of get what you're seeing now? All right. How about a catalyst? Does anybody see a catalyst up there? Or what we could technically classify as a catalyst based off of the definition? Something that's there at the beginning, there at the end, but not a part of the overall balanced reaction.
The second NO2.
The second NO2, I like that. Very good. I would say this is a catalyst here because it's here, so that's going to cancel out, and we only have one NO2 in our overall balanced reaction. So yeah, the second NO2, I would definitely say, or one of the NO2s, is acting as a catalyst here. All right, so far so good. We got that down. Now let's talk about the slow step, and what does that mean? It's called the rate determining step, or RDS, the rate determining step. The rate determining step is the slow step, because you're only as fast as your slowest step, right? So you're only good as your weakest link here. Well, your speed is going to be determined based on which step in the series is the slowest. So the slow step is called the rate determining step. And that's why it's important that they have to tell you which one is the slow step in order to be able to write the rate law. Now they could give you the mechanism and the rate law, and then you have to figure out which one is the slow step. That's a different variation, but here we don't know the rate law, so they had to tell us which of the two steps in the mechanism was actually the slow step. So let's take a look at this. Slow step's the first step. The second step is the fast step. So we're going to pay attention to the first step. Identify the reactants in the slow step. So let's do that. Our reactant, NO2, NO2. Those are our reactants in our slow step, the RDS, the rate determining step. Second thing we do, determine how many number of moles of each reactant in the slow step. So how many moles of NO2 do we have there? How many moles of NO2 do we actually have there in that slow step? 2, yes, we have this one and this one, so we're going to have 2 of them, exactly right. So basically, in the slow step, the number of moles is going to actually turn into the power on our concentration for writing out our rate law. So really, that's all we care about is the slow step. We ignore the rest of it, and we just write out our rate law. Rate equals K. Here is our reactants of our slow step. Concentration of NO2. And since there's 2 of them, it's second order. So because that one has 2 moles and it's the rate determining step, that means the NO2 is going to be second order here. And that's how you would find the rate law. It's very easy when the slow step happens to be the first step. Gets a little bit more complicated when the slow step is actually the second or the third step. get there, good question. How do we know that NO3 is the intermediate? Because it is formed, it is a product of the first step, and it is consumed, or it's a reactant of the second step. So we have the intermediate is formed and then consumed. A catalyst is opposite. It starts out as a reactant at the very first step, and then it ends up being a product at the end of the second step. So it cancels out. Good question. All right, so let's look at a potential energy diagram where there's a two-step mechanism here. So we're still focusing on our previous deal. As you can see, this is the NO2 reacting with the NO2 right here. You can see the little particles at the top of this graph here, NO2, NO2. All right, the first step is the slower than the second step because the activation energy is higher. So you see it has two hills now because the mechanism actually has two different transition states, two different steps to it. But we know that this is the rate determining step because its activation energy is higher. It's larger. And it's the slow step. First step in this mechanism is the rate determining step. The rate law of the first step is the same as the rate law for the overall reaction. That happens when the rate determining step or the slow step happens to be the first in the series. So that last statement applies to when the slow step or the rate determining step is the first one of the mechanism. It is always going to be the rate law for the overall reaction. In that particular case, when the slow step is the first one. As you can see, the second step, I can't remember exactly what was reacting there, but as you can see, this hill is a lot smaller. That's why we call this the fast step, because it doesn't need as much energy to do that part of the mechanism. So, because we just looked at a two-step mechanism and its potential energy diagram, what would a potential energy diagram look like if there was a three-step mechanism? What would you see there? What would the graph look like if it had three steps in the mechanism instead of two? Three hills, exactly. So it looks something like that. Now, my question to you here, this one's taking place in three steps, has three hills. We have the activation energy of the first step there. The second hill too, that's going to be the activation energy of the second hill. We know the first step is fast. Actually, out of all of them, which step is going to be the slow step? Which one's the rate determining step? The second one. Why do we know that the second one's the rate determining step? Because it requires the most energy, the most activation energy. Exactly right. So the second step is the rate determining step. We know that one's the slow step because it has the most activation energy. And then the third step is also considered fast because it has lower activation energy. So the third step and the first step were both fast because they have the low activation energy in comparison to the second step, which has the higher activation energy. So the rate determining step is going to be the middle one, or the slow step. The RDS, rate determining step. Now, intermediates are present in between, down here, at the little bottom of the hills in between. That's where you're going to find your intermediates. And remember, I said the intermediates are unstable. They're kind of fleeting. They don't stick around very long because they're not very stable. The activated complexes are the transition states, of course. That's the top of the hill. That's that maximum amount of energy to get the bonds breaking and forming at those particular stages of the mechanism. So let's talk mechanism requirements. Is a proposed mechanism going to be accepted? It has to have a few things in order to be accepted. One thing, the elementary steps must add up to the overall reaction. The other thing is it must experimentally agree with the rate law, and you would do like the initial rate method to determine that. So it must agree experimentally, and it must give the overall balanced reaction when you add the steps together. So this is a good stopping point. We will finish this on our next class.